All right, hello and welcome back to the second part of week 4. As promised last time, in this segment, we are going to be talking about how you can actually compute a maximum flow. So we are going to design an algorithm that computes a max flow. And we are going to actually begin by formalizing the intuition that we had last time, which is that the maximum flow is actually upper bounded by the capacity of a minimum cut. What we said last time is that if somebody shows you a ST cut which has a certain capacity, let's say you have a ST cut whose capacity is 10, that means that the maximum flow that you can push from S to T cannot exceed 10 because in some sense it has to go through this cut, which is a bottleneck. Now, of course, if you have a different cut which has an even smaller capacity, then that's an even better bound. So in particular, the minimum cut gives you the best possible bound on the maximum flow as far as bounds from cuts are concerned. And what we are going to actually show is that this bound is tight, which is to say that you can actually design a flow that saturates a minimum cut in the network. So first things first, let's go over why the cuts are upper bounds for flows. So let's actually write out what we want to prove. All right, so this is what we want to show in notation. Now let's basically fix an arbitrary flow, and let's also fix an arbitrary min cut, and let's go on to show that this inequality holds. So we're going to do this step by step. So let f be this arbitrary flow that we have fixed and consider the value of f. Remember, we defined the value of f as being the net flow that comes out of the source vertex. So this is basically by definition. Now, what I can do here is basically add a bunch of zeros to this term so that we can analyze this further and move towards, well, getting an expression in terms of the cut. Remember, we want to relate the value of the flow to the value of a fixed ST cut. So let's say that the fixed ST cut that we are looking at is S comma T. So let me add here the terms del of V for all V in S. So in particular, let's look at V in S, del of FV. Notice that because the source belongs to S, this term is there in this summation, and all the other terms are 0 because, well, it's a flow, so it satisfies the conservation constraint for any vertex that is not S or T, and we know that T does not belong to S, so all the other vertices that are present in the sum must actually obey the conservation constraint, and therefore here what we have just done is we have added some zeros, and that's just by conservation. Okay, let's just write this in expanded form, meaning what are these del values? Well, it's the difference between the outgoing flow and the incoming flow. So let's write that out explicitly for all the vertices here. In fact, let me just put this down here on the next line. So what is del f of V? We want to look at all the edges that go out of V. So let's say this is V in S, and I want to look at all vertices U that are out neighbors of V, and we look at the edge from V to U, and we look at the flow in there. That's the total outgoing flow from the vertex V, and we adjust for the incoming flow into the vertex V, so that's V in S and all choices of W, but this time we're looking at edges coming into V, right? So this again is really, again, by definition. And now I want to observe here that if you think about what we are looking at, so we're looking at the net flow for vertices that belong to S. And so we're looking at all these edges that are incoming and outgoing. And some of these edges, well, they're going to land at or come from other vertices in S, but some of them are also going to land at or come from vertices outside of S, which is vertices of T. So if you think about the edges which are fully inside S, you'll notice that they show up exactly twice in this overall expression, once positively and once negatively, right? So if you have a vertex, let's say we have a vertex VU like that, then when the sum visits V, then the edge from V to U will occur with as a positive term, and when the sum is running through the vertex U, then the edge from V to U will manifest as a negative term, which basically means that it's the same term showing up twice and they all sort of cancel. But if you look at the edges that are sort of going out or that are coming in to the set S, those edges show up only once in this term, okay, once in this expression. So we might as well really just focus on the edges that actually belong to the cut, because the values associated with all the other edges are basically going to cancel off. So I'm going to say, well, let's only look at the vertices U that don't belong to S and the vertices W that don't belong to S. You can take a moment here and convince yourself that this is exactly the same thing. All that we have done is we have dropped all the edges that begin and end at S, that have both of the endpoints in S. And that's a fair thing to do because it's a collection of terms. These terms cancel out in the sum, so it's basically like saying we've subtracted 0 and therefore we leave the value unchanged. But notice also now that U not in S is really the same as saying that U belongs to T, because an ST cut is essentially a partition of the vertex set into these two parts S and T. So if you are not in S, then you're definitely in T. So we might as well write this down as U in T and W in T respectively. And now if you think about it, well, what's going on here? We have a bunch of terms that involve the flows on the cut edges, and of course all the flow that is coming into S is getting subtracted and all the flow that is going out of S is getting added, which means that a valid upper bound on this expression here is just the flow that is going out of the set S, right? So we have V in S, U in T, F of V to U, that's the flow going through these edges that are going out of S. And if you really want to be explicit about your justification, it comes from the fact that these flow values are all non-negative, right? So we are basically dropping the subtraction of a positive term. So what we are left with is a valid upper bound. Yes. So now what can we say about this expression here? Well, now let's bring in the capacity constraints to realize that, well, this is just upper bounded by the capacities of the respective edges, because we're talking about feasible flows here. So let's rewrite this, but now in terms of capacities. But now this here should strike you as a familiar expression, because this actually is exactly the capacity of this cut. The capacity of the cut we defined as basically the total amount of capacity that's available on edges that go from S to T. So this I'm going to write as the capacity of the ST cut, which we denote like this. And let me just remember that this inequality here comes from feasibility. the feasibility of the flow. So notice that we have what we want if you follow sort of this chain of inequalities and equalities here. You see that we have started from the value of the flow F and we have ended at the capacity of the cut S comma T. The choices of F and S comma T, that is the choice of flow and the choice of cut, are completely arbitrary. So in particular, if F is a max flow and ST is a min cut, this inequality also holds. So we know that the value of the flow, the value of the max flow, is upper bounded by the capacity of the min cut. That's sort of the most useful version of this inequality. And now the next natural question to ask is, well, are there flows that actually achieve these values, or are they going to fall short? And of course, we have done the spoiler on this before, so we already know what the answer is. And the answer is that indeed you can push a flow whose value is equal to the capacity of the minimum cut. And now what we are going to do next is basically devise an algorithm that actually achieves this. We will argue that it actually does achieve this next time. But for now, let's just go over the mechanics of the algorithm. Now, before I actually write out the algorithm for you step by step, let's again spend a minute thinking about, well, what would we do? And you remember we started off this course with a discussion on greedy algorithms. So here is a question to think about. What if we just started with some kind of a greedy approach? It's not entirely obvious what a greedy approach would be here. One thing is we can go to every edge and say, okay, look, if your capacity is 100, I'm going to assign to you a flow of 100. That seems like the greediest thing that you can do if you want to maximize the flow. But of course, the trouble with doing this is that capacities have no obligation to, follow the conservation constraint. So you may have a junction where you have a bunch of outgoing edges, which are, let's say, fairly high capacity. But then you have only one incoming edge, and let's say that's a low capacity edge. And if you were just being greedy here and trying to max out all of these links, then you're going to end up with a flow that's very much not a flow, right? Because it's going to violate the conservation constraint. Okay, so we have to be careful about the greedy algorithm not only being optimal in its output, but even before that, it has to actually produce output that makes sense. It has to be valid output. So first, we need to find a way of coming up with something that at least looks like a flow and is feasible, and then we can talk about whether it is optimal, right? And here's like a natural way of coming up with a feasible flow. It's somewhat going back to what we discussed last time as well. So let me draw a network here just so that we can work with an example. All right, so here is an example of a network complete with capacities and so on. And if we were to try and think about a natural way of constructing a flow that respects both conservation and capacity constraints, then one way to do it would be to say, hey, let's try and find a way to push material along a ST path. So this is something that we did briefly when we were doing examples last time. So for instance, here is an ST path. We go from S to this vertex above, and I don't have labels at the moment, so let me assign some. We have A, B, C, D. So here is a ST path. We go from S to A to C to D, and then finally to T. And I'm tempted to push flow along this path, and for the flow to be feasible, I know that, well, I have to respect all the individual capacity constraints, and I also have to satisfy simultaneously the conservation constraint. So natural thing to look for is the edge that has the smallest capacity on this path and actually push that amount of flow along the entire path. I know I cannot do more because that's the limit that I'm stuck with on those edges. And let me just try and give that a shot, right? So we have the bottleneck edges being right here with a capacity of 10 each. So let's try to max out what we can push by actually pushing 10 through all of these edges along the path. So the numbers in blue denote the flow, the current flow anyway, and the numbers in red denote the capacities. Yes, so this so far is a valid flow. Any flow that has not been mentioned yet can be thought of as a zero flow. I mean, the flow is avoiding all the remaining edges right now. And well, I mean, you could ask yourself if you can push some more flow from S to T by looking for, other paths. So if edges are completely saturated, I'm going to pretend that they don't exist. So these edges, as far as I'm concerned, don't exist right now because there's no hope of pushing any more flow through these edges. But look, here is, for instance, another ST path where the bottleneck edge has a capacity of 5. So I could try to push a flow of 5 along this entire path here. So we have 5 more on the edge SA, that would be a total flow of 15. And we have 5 on the edge AB and 5 on the edge BT. Okay. And once again, this leaves us with a situation where the edge AB vanishes because, well, that's now fully saturated along with the other 3 edges that remain. Okay, so it does appear that at this point we are stuck. In fact, let me see what the network looks like with these edges removed. So let me make a copy of this and actually delete these edges. So now this is what the current network looks like, and you can see that there are no more ST paths to push flow along, and we have actually managed to push out a total flow of 15. That's the value of the flow that we came up with at the end here. And well, notice that this value is also the capacity of a certain ST cut. And well, what cut is that? So remember, a cut is simply a partition of the vertex set into S part and a T part, and I'm going to try and highlight those parts here. So what about we pick up S, A and C for the first part, and the rest become the T part. So well, what's the capacity of this cut? There are only 2 edges going across from S to T, and so those would be the edges AB and CD, and they have a total capacity of 5. So we in fact seem to have a flow that fully saturates a cut, and this of course is a minimum cut, because if there was a smaller cut, then we couldn't have possibly come up with a flow that has this value from what we have already seen. So we already know that this is in fact a minimum cut, and therefore we can also conclude that this is a maximum flow. Now, as usual with greedy, we have the eternal question of whether we just got lucky or whether this is something that is guaranteed to always work. So here is the sort of the greedy flow algorithm. So to begin with, we initialize the flow on every edge to be 0, and then we say, well, while there is a ST path, increment the flow on the path by B, where B is the sort of the bottleneck capacity on the path. It's the capacity of the edge that has the least capacity on this path, and if there are multiple edges, it doesn't matter really. But just look at all the capacities that you have on this ST path and pick the smallest. That's the bottleneck capacity. So you increment the flow on all of these edges in this fashion. I'm going to also remove the saturated edges. And we also want to adjust capacities so that the current capacity becomes basically the older capacity minus the flow. Or at every stage, what you know is that if you have a certain amount of flow going through an edge, then the remnant capacity is simply the original capacity of that edge minus the current flow. And the saturated edges are the ones where the residual capacity is zero, and for us these edges are useless because we can't pass any further flow through them, so we simply get rid of them. And then we repeat this process. As long as we can find these ST paths, we keep pushing flow along them to a point where we're left in a situation where there are no more ST paths available to us at all and we can't push flow anymore, and then we propose this as being the maximum flow. This is a good place to pause and think about whether we have done a good job, whether this greedy algorithm will actually produce the right output all the time or not. In fact, this is also like one of the assignment problems, so I'm not going to give it away completely here, but I will say that it turns out that you do have to be careful. That the example that we saw, we were very lucky, but if you spend some time, you'll perhaps be able to come up with examples where you're not as lucky, and you could just like have a really bad choice for the first path, which somehow eliminates a lot of other interesting things that you could have done. Okay, so for now, take my word for it or spend some time on it yourself to believe basically that this algorithm is not going to give you a consistently optimal answer on all inputs, although for whatever it's worth, it does always produce a valid flow. It satisfies conservation, it satisfies the capacity constraints, so you always have a valid and feasible flow, but it may not be the best in terms of its value. Okay, so even without being explicit about examples, you can imagine that one of the issues with this algorithm is that even if you made bad choices, by getting rid of these edges here, you have basically taken out any possibility for fixing the bad choices, because once edges get saturated, they simply go away, and there is no way to like hit an undo button on what you have just done, right? So what we are going to do is basically try and go with this approach of pushing flow along a path, but we are going to try and do it carefully. We are going to empower ourselves with an undo functionality, which ensures that, well, even if you didn't do the right thing or you didn't have a good choice of path, there is a way that you can basically push flow in reverse so that you can fix your mistakes and then do the right things eventually. Okay, so to be able to describe this algorithm, the one that actually does work, we need this concept of a residual graph. So what is a residual graph? It's a graph where, well, just like we said before, we adjust for the capacities to account for the current flow. So the capacity of an edge is not just the given capacity of the edge, it's the given capacity with the current flow subtracted. So that's where the word residual comes from. But you might say, oh, well, we did have residual capacities before. We adjusted for the capacities by reducing the capacity by the current flow. And that is indeed true, but the residual graph is actually more than just these adjustments. Like I said, the residual graph is a way of giving ourselves the power to undo flow that we have sent in a previous step. And the way we are going to introduce the undo button is by allowing for flow to flow in reverse, if you like. So let's actually take a look at how the residual graph is constructed through an explicit example. So we have our flow network back here with the capacities, and the residual graph is going to be essentially the same graph with the capacities updated to adjust for flow as before, but now interestingly, we are also going to bring in edges that point backwards, and that's what makes the residual graph special. So these edges that are pointing backwards are, of course, artificially introduced edges. They don't exist in the physical network, and they symbolically represent the undo business that I was talking about. So the edge that goes in reverse will have a capacity that is actually equal to the flow, because, well, that's hopefully intuitive. If you want to push flow through, one of these artificial edges, that's essentially representing the idea that you want to take back some of the flow that you are actually pushing through the physical edge that's actually present in the original graph, right? So that's kind of the, in my opinion, beautiful idea of a residual graph. So we have all of these sort of extra edges that are thrown in here for good measure, and let's just imagine that we have, a flow of 5 units going through this path on the top, and everything else is a zero flow, right? Then what would the residual graph capacities look like? Well, let's focus on these edges one by one. So if you look at this edge from S to A, it had an original capacity of 20, but now we have a flow of 5 units going through it. So the updated capacity is going to be 15. But now this reverse edge from A to S gets a capacity of 5, because that's the amount of flow we're actually pushing. So if you want to pull some of it back, then in the residual graph, that's going to be the same as saying, well, send a flow of, whatever amount up to 5 from the edge, through the edge A to S. And the way you interpret that with respect to the original flow in the original graph is, okay, if I'm sending 3 units of flow in the edge from A to S in the residual graph, then that's the same as saying reduce 3 units of flow in the edge from S to A in the original graph. Okay. Now, what about the edge A to B? Well, that's now fully saturated. It had a capacity of 5 and there's a flow of 5. So the residual capacity is 0. But on the reverse edge, we want to give you full freedom to pull back any amount of this flow that you want. And for the last edge, again, from B to T, we are similarly going to have a revised capacity of 10 and a reverse capacity of 5. So notice that all of these sort of reverse edges here ended up getting a capacity of 5, representing the original flow. Now, everywhere else, the capacities stay untouched, and the artificially introduced edges have a capacity of 0. This is assuming we are working with the flow that is simply 5 on all of these edges and 0 everywhere else. This would be the residual graph associated with that. Okay. And now what we are going to do repeatedly is look for S to T paths in the residual graph, and that may be a mix of some of the black edges and some of the green edges. And we are going to transform this into a flow for the original graph, where of course the green edges don't exist, by saying that whenever you have flow going through a green edge, that basically means reduce the flow going through the corresponding original edge by whatever amount of flow you're sending through the green edge. Okay, so for instance, if we had, let's say, a ST path which looked like this, and let me put down some capacities here, and these are capacities from the residual graph. And let me put down some flow here. Let's actually do a bottleneck flow. Now, what does this mean for the original graph? Well, these edges are simple because, all we are saying is the edge from S to A has a current residual capacity of 10, which means whatever the original capacity was for the edge S to A probably already have some flow going through it, but we still have 10 units of capacity remaining, and I want to use up 3 more units of that capacity. So I'm going to augment the original flow value through the edge S to A by another 3 units, right? And that's the same for most other edges except the edge from B to C. The edge from B to C is a reverse edge. It's one of the artificially introduced edges, which means that the edge we should be really paying attention to is the edge from C to B in the original graph. The fact that the BC edge in the residual graph has a capacity of 3 implies that the flow that we had going through this edge from C to B must have been of 3 units, right? So this was the original flow, and the fact that we are passing a flow of 3 units through the edge BC in the residual graph is basically the same as saying, well, let's cut this flow out from the edge C to B in the original graph. So I just want to basically transform the original flow by getting rid of this flow completely, right? And this is exactly what I meant by the fact that these back edges or the artificial edges in the residual graph basically empower you with an undo button. You can, whenever you send flow through one of these artificial edges, you're basically reducing the amount of flow that you had originally sent in the real graph, right? And so you're adjusting the flow that you came up with, not only in the sense of incrementing or augmenting it, but whenever required also decrementing it or reducing it, right? So that's what we do with the residual graph. Let me actually formally define the capacities on the residual graph and also how we do the flow augmentation. So here is the residual capacity. Remember that the residual capacity is always defined in the context of a flow. If you just give me a flow network with some capacities and ask me to define a residual graph, I won't be able to do it. You have to give me a flow, and it's only in the context of that flow that I can talk about residual capacity. So this subscript F here is very relevant, okay? So if you have an edge from U to V in E, that is to say this was an original edge in the graph, then the residual capacity is simply the original capacity minus the flow, right? So in particular, if this edge was an edge that was being avoided by the flow, then the residual capacity is the same as the original capacity, okay? On the other hand, it's possible that this is one of those artificially introduced edges, which means that the opposite edge is the one that is there in E. In that case, the capacity is actually going to be the same as the flow through the original edge, right? And if neither of these are true, then the capacity is simply 0, okay? So that's, well, I mean, if you're wondering what that last case was about, it's just pairs of vertices that have no edges between them in the original graph, okay? So those are the residual capacities. Now let's talk about flow augmentation. So how do we update the flow if we have a S to T path in the residual graph, right? So again, this is not very dissimilar from the greedy algorithm in the sense that we are going to find our bottleneck edge and we are going to push that much flow through this entire path. But the thing that makes all the difference is the presence of these artificial edges, which do a little more than what just the greedy algorithm is doing, and that's what lends this algorithm its correctness. So let me denote the capacity of the bottleneck edge by capital F. So F is going to be the tightest capacity that we have in our path. So let's go over all the edges in the path P. So here P is some S to T path, right? And now we want to pull up the tightest capacity, but in the residual network. That's why I'm using C sub F. And now the augmented flow is defined as follows. I'm going to call it F prime. And the way this is defined is that, well, if you have an edge in the path and that's a real edge, that's an original edge in the graph, then we actually want to increment the flow in such an edge by the amount f. So this is if uv is an e. The edge in the residual graph happened to be one of these artificial reverse edges. Well, then, like I said, we are pulling some flow back. So we go to the edge uv and actually remove f. And otherwise, well, if the edge that we are talking about is not even on the path, then the flow through that edge remains unchanged. It's just the original flow. So this is f prime, it's the augmented flow, and we want to basically do this augmentation for as long as possible. So the idea of the Ford-Fulkerson algorithm is to say that, well, as long as there is a path from S to T in the residual graph, well, just augment the flow, recompute the residual graph, and keep going. So when we get stuck is when S and T are completely disconnected in the residual graph. And at that point, we want to say that we have done as well as we possibly can, because the point where we are stuck, the residual graph naturally offers up a cut that is fully saturated by the flow. And that is why we will know eventually that this algorithm is correct. But that's not an argument that I'm getting into here. At this point, what I would very much encourage is for you to make sure that the algorithm is clear, that the notion of a residual graph is clear, the notion of a bottleneck flow is clear, the notion of how we are augmenting the flow is clear, and hopefully you have some intuition for why just the simple greedy approach doesn't work. And we really need this idea of undoing our mistakes via these reverse edges, and that's really key to this whole algorithm. So I will summarize this by saying that in this segment we have basically convinced ourselves that cuts are upper bounds for flows, and we have seen why a natural greedy algorithm that just pushes flows along ST paths and adjusts capacities doesn't quite work. We saw how we can modify this approach by introducing some undo features with a residual graph, and we saw the mechanics of what is now known as the Ford-Fulkerson algorithm for computing max flows. But the only thing we haven't done at this point is actually reasoned about why this algorithm is actually correct. So that's a discussion that we will have next time. But until then, please go over a few examples, try to dry run the algorithm on some small graphs yourself, and get a feel for the fact that it works, so that when we come back and discuss a proof, it hopefully clicks and falls in place nicely.